Okay, so in the last class we discussed about the interference of light. Now today we will discuss the diffraction of light and polarization of light. So let's begin. So what is diffraction of light? So diffraction is phenomenon of bending of light around the corners of an obstacle. Okay, so for an example, suppose this is a light which travels in this direction, suppose. Okay, so these are light rays, or you can say light waves. So they are traveling towards right and they fall. So suppose some obstacle comes, then what will happen? The light will bend like this along the corners of obstacle in different directions. Okay, bending of light around the corners of an obstacle. Now this diffraction gives rise to certain pattern. Okay, so this diffraction gives rise to certain pattern. So that is known as diffraction pattern. Now it would be similar to that of the interference pattern, but the phenomenon that happens here, it's different. Okay, so the obstacle here is you can consider it to be one slit. Okay, so interference pattern is caused because of what? Two slits. Diffraction pattern is caused because of one slit. Okay, so we'll talk about that. So now there are two kinds of diffractions. First is the Fresnel diffraction, and here the source and screen are at finite distance. Okay, so in Fresnel diffraction pattern, the source and screen are at the finite distance, and in case of Fraunhofer diffraction, the source and screen are at infinite distance. Okay, so now let's talk about diffraction due to a single slit. So here you have a light which is traveling towards right. Okay, so these are light rays or light waves, you can say. They are traveling towards right. So here we keep one slit. So there is a cardboard and there is a small slit, small opening is in that cardboard. Okay, so that is a slit, right? So what happens here? See, so here these light rays, they are bending around the corners. Okay, these light rays are bending around the corners of this obstacle. Okay, and then suppose we make use of this lens to focus these light rays on the screen. Okay, so now see what happens here. If you consider a point over here and point over here, so there would be some path difference between the light rays that are bending from this end and light rays that are bending from this end. Okay, there would be some path difference between the light rays that are bending from this end and that end. So that path difference would be equal to a sine theta. Now what is a? A is the size of the slit. You can see this is size of the slit, that's a, suppose. Okay, so now to find out the path difference between the rays, what you do is you draw a perpendicular from here, okay, on this ray. So this ray is traveling this much extra distance, right? Okay, if you consider a point which is slightly above the center on the screen, right? If you consider a point which is slightly above the center from this slightly above the center on the screen. Okay, so this much is the path difference. So now if light rays are bending with an angle theta, so you can see this is angle of bending. Okay, angle through which light rays are bending. So this angle and this angle would be equal. Okay, can you see that this angle is theta? Okay, this angle would also be equal to theta. Why? Because you can say this is a wave front. Okay, so waves are perpendicular to wave front, right? So now if light waves, they were traveling in this direction, then the wave front was like this. Okay, this is direction of propagation, so this is a wave front. Okay, so angle between them is 90 degrees. Now suppose the light rays bend, or you can say waves bend, and they travel like this. So in this chapter we are talking about waves only. So these are light waves traveling in this direction, and this is just a direction of propagation. Okay, but these are waves. So here the wave front would be like this, right, perpendicular to direction of propagation. So this is the direction of propagation, earlier direction of propagation, and this is the wave front. Okay, angle between them is 90 degrees. right? So then the direction of propagation changes like this, okay? So direction of propagation changes by an angle of theta. So wavefront will also change by angle of theta only, okay? Because wavefront is what? Perpendicular to direction of propagation. So this angle is also theta. This thing is clear, everyone? Right? So then you can find out the path difference. So this is suppose A, this is the hypotenuse, then you draw a perpendicular from here. So this is perpendicular. This much is the path difference. You can call it delta x. So you can say sine theta is equal to what? Opposite side. This opposite side divided by hypotenuse. So that is delta x divided by A. Okay. So sine theta is equal to delta x divided by A, and therefore delta x would be equal to A sine theta. So that is the path difference. Okay. So you can say if light bends through an angle of theta, then what would be the path difference between the light that is coming from this edge, okay, or which bends around this edge and which bends around this edge? The path difference is equal to what? Path difference is equal to A sine theta, okay, and A is the width of the slit. Is this thing clear to everyone? Yes, no? This is very important. So now I'm going to explain an important point. So see this, the path difference we have seen delta x is equal to what? A sine theta. Then now what was the condition for path difference for constructive and destructive interference in case of Young's double slit experiment? So if path difference is equal to what? Path difference is equal to 0, lambda, 2 lambda, that is integral multiples of lambda, integer multiples of lambda. Then there used to be constructive interference, okay? And if path difference was odd integer multiples of lambda by 2, okay, lambda by 2, 3 lambda by 2, 5 lambda by 2, so on and so forth, there was a destructive interference. So the condition is exactly opposite here, okay, and we'll understand why. So a path difference between the light waves bending from the top and bottom edge is equal to n times lambda, then the point on the screen would be dark, and if the path difference is 2n plus 1 lambda by 2, then the point would be bright, okay. If path difference is equal to n times lambda, then the point would be dark, and if the path difference is 2n plus 1 lambda by 2, then the point would be bright, okay. So now let us try to understand this. So the diffraction pattern that you will see for a circular slit, it will look like this, okay. So you will always have a central bright fringe, okay. So central bright circle, let's say, then there would be first dark fringe, okay, then next white fringe, next dark fringe. White meaning it won't be white, okay, we are using monochromatic light. So whatever is color of that light, okay, this is the color of this color would be same, okay. So this is bright and dark. So see the first condition. Now let's imagine that the path difference between the light that's bending from this edge and this edge, it's equal to lambda. That means how much is delta x? Delta x is equal to lambda, okay. So now this is the wavefront, and according to the Huygens principle, all points on this wavefront, they behave like what? They behave like secondary sources of light, right? All points on the wavefront, they behave like secondary sources of light, okay. So there would be waves coming from this point, this point, this point, this point, this point. These are all the waves, light waves, okay, coming from each and every point on this wavefront, right? So then suppose all these light waves are bending through the same angle, okay. So then now path difference between this wave and this wave is suppose lambda. So what would be the path difference between this wave and a wave over here exactly at the half? It would be equal to lambda by 2, right? This thing is clear. The path difference between this wave and this wave is equal to lambda. How much would be the path difference between a wave over here and here? It would be exactly half. Okay, this thing is clear? Yes, no? So then what we can do is we can imagine that there are n number of sources. Okay, we can imagine that there are n number of sources. So let's say there are 100 sources, or for simplicity let's take 5 sources in upper half. Okay, so 1 2 3 4 5. Okay, so they would be symmetrically placed. So 5 sources in upper half and 5 sources in the lower half of the screen, right? So then now you can consider this source. Okay, this is a point source of light, and for this point source and this point source, how much is the path difference? Okay, for light wave coming from this point source and the light wave that is coming from this point source, the path difference would be equal to lambda by 2, because path difference between this and this one is lambda. So between this and this one it would be lambda by 2. Path difference between this one and this one would be equal to lambda by 2. Okay, then path difference between this one and next one would be equal to lambda by 2. So for each light wave that's coming from top half of the slit, there would be a light wave coming from the bottom half of the slit, where the path difference between the two waves would be equal to lambda by 2, and therefore there would be a destructive interference between them, and therefore the point would be dark. Okay, so each wave from the top will be matched by a wave from the bottom half. Okay, each wave from the top half would be matched by a wave from the bottom half, right, where the path difference between the first wave and the second wave, that is wave from the top and wave from the bottom half, would be equal to lambda by 2. And therefore if you add up them, I mean if you consider this wave and this wave only, so the interference due to them will give rise to what? A dark point. Okay, then interference due to this wave and this wave, it will give rise to a dark point, and that's why there would be completely destructive interference. So point on the screen would be dark. Okay, so if path difference between extreme points is equal to what? That is a sin theta is equal to lambda, then the point would be dark. Is this thing clear, everyone? Okay. Yes, Yamini, is it clear? All right, good. So then that point would be dark. After that, now let's consider, so for lambda it would be dark. Similarly, you can consider if path difference between the extreme points, that is top edge and bottom edge, the path difference is equal to 2 lambda. Then you can consider the screen to be broken. Broken means divided into what? 4 parts. Okay, let's consider screen to be divided into 4 equal parts. So here the path difference between this and this edge is equal to 2 lambda. Then path difference between this and this point would be equal to lambda. Then path difference between this and this one, okay, would be equal to what? Lambda by 2. So you can consider that for waves in this part, there would be waves from this part. There the path difference would be equal to lambda by 2 and lambda by 2. Okay, so all sources in this part, this region, they are matched by sources from this region, which emit the waves with path difference equal to lambda by 2, and therefore the point would be dark. Okay, similarly, okay, here the path difference from this point and this point is lambda. Okay, so sources from this part are matched, point sources from this part are matched by point sources from this part, where the path difference is equal to what? It's equal to again lambda by 2, and therefore again there would be destructive interference and the point would be dark. Okay, So for 3 lambda, you can imagine the slit to be divided into 6 equal parts. Okay, so on and so forth. So if the part difference between the top edge and bottom edge is equal to what? It's integer multiple of lambda, then the point is going to be dark. Okay. Now let's see what happens to odd integer multiple of lambda by 2. Okay, odd integer multiple of lambda by 2. So see here, so if it is let's say 3 lambda by 2, then you can imagine that screen to be divided, not screen, the slit to be divided into 3 equal parts. Okay, so if it is lambda by 3 lambda by 2, part difference between this edge and this edge is 3 lambda by 2. So then let's consider the slit to be divided into 3 equal parts. So part difference between this and this point then would be equal to what? Lambda, right? It is 3 lambda by 2, no? So part difference between this and this point, it would be equal to lambda by 2. This and this would be equal to lambda by 2. This and this would be equal to lambda by 2. Now consider the first two regions of the slit. So for each wave in this region, you will get a wave from this region. That is, sorry, for each source in this region, you will get a source from this region, which will send waves at the part difference of lambda by 2, right? So for each wave in this region, you get a wave. Again, I said wave. For each source in this region, you will get a source from this region, which will send the waves at part difference of lambda by 2. So there would be destructive interference between the waves that are coming out of sources from this region, point sources from this region, and waves that are coming out of point sources from this region. Okay, so there would be destructive interference between these sources and these sources. Okay, and that's it. Now, so these sources, the waves due to these sources are cancelled out by waves due to these sources. But then these many sources are still left. So they will send, okay, they will also send waves towards that point, let's say. Okay, so then what will happen to these waves? So there can't be a destructive interference because part difference between this and this point itself is lambda by 2. But then if you consider this to be divided into 2 equal parts, so part difference between this and this point would be equal to what? Lambda by 4. Then for each source in this region, you will get a source from this region where the part difference would be equal to lambda by 4. So it is not exactly constructive interference, but neither a destructive interference. So point will not be completely bright, it won't be completely dark. Okay, is this thing clear? Yes, no? So we say this is, you will get a bright band over there, but that bright band will not be as bright as the bands they are formed in the Young's double slit experiment. Okay, so intensity won't be that much. This thing is clear, everyone? All right, good. So then see, at the center there will be always a bright band. At the center there would be always a bright band. Because of what? Because the light that's coming from this edge as well as this edge, okay, they will travel equal distance to reach at the center. So there won't be a part difference for the points for the light waves that are coming to the center. So at center there would be always a bright band, but then it will be followed by a dark band and a bright band, so on and so forth. Okay, right? So now we need to remember these conditions that we have just seen for nth secondary maximum. What is the part difference? Part difference is, suppose, a sine of theta suffix n. Okay, for nth secondary maximum, not the central maximum, other maximum. So what is the part difference? It is equal to a sine theta suffix n, and that is equal to 2n plus 1 lambda by 2. Okay, central can be called as 0th maximum. Okay, others are 2n plus 1, others are nth maximum. So the condition for part difference for them, it is equal to what? 2n plus 1 lambda by 2. Okay, so a sine theta is the path difference, we put suffix n. So a sine theta for nth band, it is equal to 2n plus 1 lambda by 2, where n can take values 1, 2, 3, so on and so forth. Then condition for secondary minimas is the path difference would be equal to a sine theta suffix n, okay, n for nth minima, so that's equal to n times lambda. Okay, so please remember these conditions. They are exactly opposite to that of what? The Young's double slit experiment. Okay, and then what would be the width of central maxima? So width of central maxima, width of okay, this is secondary maxima. This is width of secondary maxima or minima. It is just equal to that of you can see the formula, it's just similar to that of Young's double slit experiment. So beta is equal to lambda times d by a. So lambda is the wavelength of light. What is d? D is the distance between the source and screen, that is slit and screen. Okay, it is this distance is d. So sometimes you will make use of a lens only. Okay, so in that case the d will become the focal length of the lens. Okay, that formula will get modified to what? Lambda times f by a. Okay, so then a is what? A is the width of the slit or size of the slit. Okay, so sometimes we make use of a lens. Okay, so then the lambda the formula gets modified, that lambda times f by a, right? So this is the width, which is similar to, this formula is similar to the fringe width in the Young's double slit experiment. Okay, just width of the slit here would be what? It corresponds to the distance between two slits in that formula. Okay, so what would be the angular width? Angular width theta is equal to lambda by a. Okay, just divide this beta by d, so we get the angular width. Angular width is equal to lambda by a, right? Then width of the central maxima, it is equal to 2 times of beta. Width of the central maxima is equal to what? 2 times of beta, right? So it is equal to 2 times of lambda d by a. Okay, or it is 2 times lambda times f by a. And what would be the angular width of the central maxima? So it is 2 times of lambda by a. Okay, this thing is clear? Yes, no? Now you might ask, why is the width of central maxima this much? So see, what is condition for the first secondary minima? So path difference should be equal to what? Path difference should be equal to lambda. Okay, so where is the first secondary minima formed? So first secondary minima will be formed at lambda times d by a on upside and lambda times d by a on the downside, right? Okay, so if this is the center, what is the distance of the secondary minima? First secondary minima, it is lambda times d by a on this side and lambda times d by a on this side. So that's the width of the central maxima. Is this thing clear, everyone? Okay, so now let us see some problems based upon diffraction pattern. So let's see this one. A linear aperture whose width is 0.02 centimeter is placed immediately in front of lens of focal length 60 centimeter. That means there is no separation between the slit and the lens, right? Okay, so the aperture is illuminated normally by a parallel beam of wavelength 5 multiplied by 10 raised to minus 5 centimeters. The distance of the first dark band of the diffraction pattern from the center of the screen is, tell me, what is distance of the dark band here? So x is equal to lambda times d by a. Okay, so here we make use of a lens which is kept just after the aperture, okay, or you can say the slit, and that's why there is no distance between the aperture and the lens. So this d will become what? It becomes the focal length of the lens. Okay, so we have lambda times f by a, this would be the formula, and then it's very simple, we can just substitute values. So what are the values? Wavelength is 5 multiplied by 10 raised to minus 5. So 5 times 10 raised to minus 5 in centimeters. So let's convert it to meters. 5 times 10 raised to minus 7. Okay. What is focal length? Focal length is 60 centimeters. Actually everything is in centimeters and answers are also in centimeters. So we can keep it as it is. 5 times 10 raised to minus 5 centimeters. What is D or focal length? Focal length is 60 centimeters. So it is 60 divided by A is 0.02. Okay. So that is 2 multiplied by 10 raised to minus 2. 60 by 2 is what? It is 30. 10 raised to minus 2 to the numerator becomes 10 raised to plus 2. So this is 10 raised to minus 5 plus 2 means 10 raised to minus 3. 30 times 5 is 150. 150 into 10 raised to plus 3. Okay. So this is equal to 150 multiplied by 10 raised to minus 3, sorry, minus 3 centimeters, and that is 0.15, no? So 0.15 centimeters. So that is the answer. It's option D. Right? Very simple. Okay, yes, no. But we need to remember here for the first dark, what would be the formula? For n dark, x is equal to n times lambda d by A, just opposite to the Young's double slit experiment. Right? Let's see next one. In a diffraction pattern due to a single slit of width A, the first minimum is observed at an angle of 30 degrees when the light of wavelength 5000 angstrom unit is incident on the slit. The first secondary maximum is observed at an angle of. This is the question. So tell me. Alright, so we have condition for the part difference, right? So part difference, delta x is equal to what? A sine theta. Okay. So for which maxima? No, it was minima. First minima is observed at 30 degrees. Okay. So for first minima, we can say the part difference A sine theta is equal to what? Tell me. Lambda or lambda by 2. What is it? For first minima in diffraction pattern, what's the part difference? It's lambda, right? Very good. So it is lambda. And then for first secondary maxima, what's the part difference? So for first maxima, we want to find out that angle. So A sine theta 2 is equal to what? 2n plus 1. Okay, for nth maxima it is 2n plus 1 lambda by 2. So here n is equal to 1. So it would be equal to 3 times of lambda by 2. So this is your equation 1. This is equation 2. Divide 1 by 2 or let's divide 2 by 1. Right. So 2 by 1 will give you what? A sine theta 2 divided by A sine theta 1 is equal to 3 lambda by 2 divided by lambda. So that lambda gets cancelled out. So it is 3 by 2, right? And what is so A also gets cancelled out. What is theta 1? So theta 1 is 30 degrees. What is, okay, sine theta 2 is equal to 3 by 2 times of sine theta 1, right? Because lambda and lambda got cancelled out. What is theta 1? Theta 1 is 30 degrees. So put value of sine theta 1, that is sine 30, that's half. So this is equal to what? 3 by 4. Okay, that's sine theta 2, and therefore what would be theta 2? It is sine inverse of 3 by 4. Okay, so it is option B. Is this in clear? Let's see next one. In a double slit experiment or double slit experiment, right? The two slits are 1 mm apart and the screen is placed 1 meter away. Okay, a monochromatic light of wavelength 500 nanometer is used. What will be the width of each slit for obtaining 10 maxima of double slit within the central maxima of the single slit pattern? Okay, so the question is, in a double slit experiment, two slits are 1 mm apart and screen is placed 1 meter away. A monochromatic light of wavelength 500 nanometer is used. Okay, what will be the width of each slit for obtaining 10 maxima of double slit within the central maxima of the single slit pattern? This is the question. What should be the width of each slit? Okay, so it's given for double slit case, double slit, D is given, right? D is equal to 1 mm. Okay, then screen is placed at 1 meter and wavelength is given, wavelength is 500 nanometers. So what they say is, what would be the width of each slit? We want to find out width of the slit. Okay, so what is A is the question. If what happens for 10 maxima of double slit, okay, 10 maxima of double slit fit within the central maxima of single slit. Okay, so we can just say that 10 maxima of double slit is equal to maxima, central maxima. It's option C. Let's check. Central maxima of single slit. Okay, so this would be equal to 10 times of lambda times capital D divided by what? A. Okay, and what is width of the central maxima? So it is 2 times of lambda D divided by width of, okay, this would be D, right? 10 times of lambda capital D divided by distance between two slits, and this is 2 times of lambda D divided by A. A is width of the slit. Okay, so lambda D and lambda D gets cancelled out. Okay, then this is 10 by 2 is 5. So what do we get? A is equal to, if we take reciprocal, it's just equal to D by 5. A is equal to D by 5, and that's equal to what? D is 1 mm, 1 divided by 5, so that is 0.2 mm, correct. So that's the answer. Very simple, right? Yes, no? Okay, good. Let's see next one. At the first minimum adjacent to the central maximum, first minimum adjacent to central maximum of single slit diffraction pattern, the phase difference between the Huygens wavelength from the edge of the slit and the wavelength from midpoint of the slit is. Okay, so now this is deeper question, right? So for this kind of question we need to understand what's happening there. Okay, so for the first minimum central, for the first minimum adjacent to the central maximum, the phase difference between the Huygens wavelet from the edge of the slit and wavelet from the midpoint of the slit is. Tell me. So if I draw that slit, okay, so phase difference between this point and this point, this is your slit. Tell me. You consider waves from here and waves from here. Then for first minima, what should be the path difference between them? So if A is the size of slit, this is A sine theta, and for first minima, or this is delta x, for first minima, delta x must be equal to what? it must be equal to lambda. Okay, but we don't want the phase difference between this and this point. We want phase difference between, let's say this point is A, this point is B, this point is O. So we want phase difference between A and O. So what would be path difference between A and O? Path difference between A and O, it would be half of the path difference between A and B, right? So that is equal to, for waves starting from here and here, the path difference would be half of the waves between this and this point, right? Waves starting from this and this point. Okay, so this path difference would be equal to delta x divided by 2. So that is lambda by 2. Okay, path difference between A and O is equal to what? It's equal to lambda by 2. And then you can tell me what would be the phase difference. Yes. What's the formula? Yeah, phase difference, it must be pi, right? Very good. So we know phi is equal to what? 2 pi times delta x by lambda. Just substitute delta x is equal to lambda by 2. It is 2 pi by lambda multiplied by lambda by 2. Right? So this thing gets cancelled. So phase difference is pi. Good. Right? So this is also simple. If we understand it, it's very simple, right? Okay. Let's see next question. A beam of light of lambda equals to 600 nanometer from a distant source falls on a single slit 1 mm wide, and the resulting diffraction pattern is observed on the screen 2 meter away. The distance between first dark fringe on either side of central bright fringe is. So they are asking distance between first dark fringe on the either side. Okay, so this is central bright and this is the first dark. Suppose from the central bright, from the center of central bright, okay, the two dark fringes are at same distance. What is the distance? Lambda times d by a. So what is distance between the two dark fringes? It's option D. Okay, let's check. It is equal to width of the central slit, right? It's equal to width of the central slit, right? So it is equal to what? Just 2 times of lambda d by a. So let's substitute values there. It is 2 times of what is lambda? Lambda is 600 nanometers. 600 multiplied by 10 raised to minus 9 times d is 2 times 2 divided by a. A is what? A is 1 mm, right? 1 mm. So this is 2 times 2 is 4. 4 times 6 is 24. 2400 multiplied by 10 raised to minus 9. So that is 2400 multiplied by 10 raised to minus 9 is what? You can say 2.4 into 10 raised to minus 6. Yeah, this is 1 mm, no? This is 1 mm. So 10 raised to minus 3. Okay. 10 raised to minus 9, this would be plus 3. So that is 10 raised to minus 6. Okay, then this is 2400 multiplied by 10 raised to minus 6. So it is 2.4 into 10 raised to minus 3. Okay, 2.4 into 10 raised to minus 3 meters. So it would be 2.4 millimeters. Right? So Selva Kumar said 2.4 millimeters, right?
Yes, sir.
Okay, so that's the answer. Option D. Okay, this is clear, everyone? Okay, good. Let us see next one. A parallel beam of fast moving electrons is incident normally on a narrow slit. Parallel beam of fast moving electrons is incident on a narrow slit. Then a fluorescent screen is placed at large distance from the slit. If the speed of electrons is increased, which of the following statements is correct? Okay, so now see, here we make use of the wave nature of electrons, but we haven't studied about that. Okay, we'll study about that in the next chapter, upcoming chapter, that is dual nature of radiation and matter. But here the electrons behave like waves. And what is the wavelength of an electron? So wavelength of de Broglie wavelength of an electron, because this principle was given by de Broglie. Okay, de Broglie wavelength of electron. We are going to study this in dual nature of radiation and matter. Lambda is equal to h by mv. So h is the Planck's constant, and m is the mass, and v is what? Its speed. Okay, actually it's the de Broglie wavelength of any object with having mass m moving with speed v. So if speed of electrons is increased, what will happen to the wavelength? So if v increases, wavelength decreases. Okay, and then if wavelength decreases, what's the question? Angular width of the central maxima will decrease. Will it happen? Tell me, what is the angular width? Theta of central maxima. Theta of central maxima, it's equal to 2 times of lambda by a. Right, for other fringes or other bands it is lambda by a. For the central one it's 2 times lambda by a. So will it decrease? Yes, it will decrease, because lambda is decreasing, right? If speed increases, lambda decreases, so angular width of the central maximum would decrease. That's the answer. This is clear? Yes, no? Okay, so let us just read out the other options. The angular width of central maxima will be unaffected. That's not correct. Diffraction pattern is not observed on the screen in case of electrons. That is also not correct. Okay, because electrons do show wave nature, and therefore there are electron microscopes. Okay, you might have heard about electron microscopes to observe very fine objects. Very fine object meaning suppose objects of the size of 10 raised to minus 9 meters or so, we make use of electron microscopes. Okay, all right. Next is angular width of central maximum of the diffraction pattern will increase. The angular width of central maximum of diffraction pattern, it will not increase, it will decrease, no? So it is option A, right? All right, so this is understood? Yes, no? Okay, good. Let's see next one. A parallel beam of light of wavelength lambda is incident normally on a narrow slit. A diffraction pattern formed on screen placed perpendicular to the direction of incident beam. At the second minimum of the diffraction pattern, the phase difference between the rays coming from the two edges of the slit is. Tell me. Now you want phase difference between just two edges, that is point A and B. So for second minima, what is delta x? Delta x is equal to 2 lambda, and therefore what would be phase difference? Therefore phi is equal to 2 pi times delta x by lambda. Just put the values. So it is 2 pi by lambda times what is delta x? 2 lambda. So this thing gets cancelled out. So phase difference is equal to what? 4 pi. Okay, so answer is option C. Or simply you can say that part difference of lambda corresponds to phase difference of 2 pi. Part difference is 2 lambda, phase difference would be 4 pi, right? Okay, this is clear, everyone? All right, good. So then let's see next question. ray optics is valid when characteristic dimensions are much smaller than the wavelength of light, of the same order as wavelength of light, of the order of 1 millimeter, much larger than the wavelength of light. Tell me, what would be the answer? Ray optics is valid, that means wave optics is not valid, okay, and we will imagine that light is made up of, it's option D, that's correct, okay. Ray optics is valid, means wave optics is not valid, okay, and we will imagine that light is made up of rays only, okay, or we'll just consider light rays only and just disregard their wave nature. When can we do that? When do we don't need to consider or don't need to care about the wave nature of light? So the answer is much larger than the wavelength of light. Why? For an example, suppose you take a microscope, and now if microscope is very small, okay, so that its size is of the order of wavelength, then what will happen? So we know that light bends along the corners of obstacle because it's a wave, okay. Waves have tendency to bend along the corners of obstacle. Particles can't bend, right? If you think of this as particle, so maybe particle will bend this way, right? It will collide and it might go in some direction, but waves, they can bend in all directions along the corners of obstacle. So now diffraction pattern would be formed. When is it formed? So a sine theta must be of the order of lambda, okay, right? If we take condition for maxima or minima, let's say condition for minima, so for nth minima it would be equal to n times of lambda, okay. So sine theta is what? It is between 0 to 1, right? Sine theta is between 0 to 1, n is some number, okay, 1 2 3 4 so on and so forth. That means a is of the order of lambda. Then what will happen? Diffraction will happen, okay, diffraction happens, okay, and you cannot neglect the effect due to diffraction, right? But if a is very large, if a, that means size of this obstacle is very large compared to that of lambda, then you can disregard the effect due to diffraction. You can forget about that because it will be very small, right? This thing is clear, everyone? Okay, all right. Yamini, is it clear? Okay, good. All right, so the ray optics would be valid when sizes of these instruments, optical instruments, are much larger compared to wavelength of the light. Okay, let's see next one. A parallel beam of monochromatic light of wavelength 5000 angstrom unit is incident normally on a single narrow slit of width 0.001 millimeter. The light is focused by a convex lens on the screen placed in the focal plane. The first minimum will be formed for the angle of diffraction equal to. So this is very simple. So tell me, we have a sine theta. For first minimum, it must be equal to lambda, okay. So that is equal to, therefore sine theta would be equal to what? Lambda by a. So lambda is given, a is given, okay. So this is equal to 5000 angstrom unit. So 5000 multiplied by 10 raised to minus 10 divided by width of the slit is 0.001 and it's in millimeters, so 10 raised to minus 3. So what is this? This is 10 raised to minus 3 minus 3 minus 6 goes to the numerator, it becomes 10 raised to plus 6. 10 raised to minus 10 plus 6 is 10 raised to minus 4 and 5000 into 10 raised to minus 4. So it is 0.5, right? Or 5 into 10 raised to 3 and 10 raised to minus 4 means 5 into 10 raised to minus 1, okay. So it's 0.5. Sine theta is 0.5 means theta is equal to 30 degrees. Right? So again, simple question. Then let's move on to the next topic. Okay, that is polarization. So now, what is polarization? So let's understand this. See, light is made up of electromagnetic waves and it consists of electric fields and magnetic fields. They are vibrating perpendicular to direction of propagation. Okay, so suppose light is coming towards you like this, then the electric field can vibrate like this, or it can vibrate like this, it can vibrate like this, perpendicular to direction of propagation. Okay, so you can imagine this point, it's coming towards you out of your screen, right? So these are then, okay, or you can just keep your pen on that point. Okay, so the wave is coming, sorry, yeah, the light wave is coming that way, then the electric field would vibrate in this plane or in this plane or in this plane. Okay, so it's like this. Light goes in this direction, suppose the electric field will oscillate perpendicular to that. But this is one possible direction of oscillation. Oh, okay, so this is the electric field. This is one possible direction of oscillation. The electric field can oscillate in this direction like this. Okay, so it is transverse. It is transverse to the direction of propagation. Transverse means perpendicular. Okay, now if you block these vibrations of the electric field and only allow the vibration of electric field in one direction, then that is called as polarization of light. Okay, that phenomenon is known as polarization of light. What is polarization of light? It is phenomenon of restricting oh interesting, restricting the vibrations of light to a particular direction perpendicular to the direction of propagation of wave. Okay, light wave is called as polarization of light, right? Restricting the vibrations of the electric field, you can say, to only one direction perpendicular to direction of propagation. Okay, so you block all other vibrations, that is you block this vibration, okay, vibration in some other direction, and you only allow, so suppose light is moving in this direction, so you will only allow light, this electric field, to oscillate in this direction, right? This thing is clear. Okay, so this is called as polarization of light. Is this thing clear, everyone? Okay, so now the question is, how can you do that? So special kind of materials called as Polaroids are used for it. Okay, so what's there in these materials? So there are the molecular chains. These are molecular chains. Okay, these are molecular chains, right? So now what will happen if you apply some electric field parallel to the direction of chain, then what happens is some current will flow through the chain. So that component of electric field would be absorbed. Okay, that component of electric field would be absorbed, and then this component would be allowed to pass. You getting this? See, the electric field, suppose electric field is in this direction, you can resolve it along two directions, one like this, one like this. Okay, so what happens there? This electric field, you can resolve it along two components. So let's say this angle is theta, so this would be E cos theta, and this is E sin theta, right? This is E sin theta. Okay, so then what will happen? So the component along these chains would be absorbed, because due to that component of electric field, there would be some potential difference between, let's say, these 2 points, and some current will flow through the chains. Okay, so that component of electric field would be absorbed, and component perpendicular to the direction of chain, molecular chain, would be allowed to pass. And that direction perpendicular to the molecular chain, it is known as the optic axis. Okay, it is known as what? The optic axis. Okay, so now which kind of molecules are those, etc. You can search that on Google, right? So this is polarization. Is this thing clear? Yes, no? Okay, all right. So this direction along which the electric field can pass, the direction along which the electric field can pass, it is known as the optic axis, or it is also known as the pass axis of the Polaroid or polarizer. Okay, so here this axis is the pass axis of the polarizer. Okay, so then we know this is polarization. So suppose initial intensity of completely unpolarized light, that means the electric field can vibrate along any plane. Okay, so electric field can vibrate in this plane, this plane, this plane, this plane, this plane, etc., so on and so forth. And the light wave is traveling in this direction. You put a polarizer in front of it. So then what happens is the electric field will be allowed to vibrate only in one direction, that is along the optic axis of the polarizer, or you can say along the pass axis of the polarizer, right? So the intensity out of this would be equal to I naught divided by 2. Okay, intensity would be equal to I naught divided by 2, right? So completely unpolarized light and you put a polarizer in front of it, then what will happen? The intensity of the light that passes through the polarizer would be always equal to I naught divided by 2. Okay, so roughly what you can say, the electric field is oscillating in random directions. Okay, electric field is oscillating in random directions, and therefore if you find the components of electric field along this direction and along this direction, that is perpendicular to direction of propagation, perpendicular to the pass axis and parallel to pass axis, the two components would be equal, right? So the electric field is oscillating in random directions. Okay, so if you find the components of electric field along the pass axis and perpendicular to pass axis, they would be equal, right? And therefore half of the light is blocked and half of the light is allowed to pass. Okay, this thing is clear? Yes, no? Right. Okay, and then now the first polarizer is called as polarizer only. Then next one we make use of another polarizer, okay, which is known as analyzer. What will it do? It will analyze whether the light is polarized, okay, actually polarized or not. So if you keep the optic axis of analyzer just like that of the optic axis of polarizer, if they are aligned, then what will happen? Whatever light comes out of the polarizer, it will pass through the analyzer too. Okay, so intensity here will also be equal to I naught divided by 2, right? But if you put this optic axis perpendicular, if you put it like this, remember these are not molecular chains, this is the optic axis. Okay, so this is optic axis of polarizer. So these are oscillating, light is oscillating in this way parallel to the optic axis of polarizer. Now if you keep an analyzer, that means another polarizer in front of this light, then because the optic axis of this one is perpendicular to what? Vibration of the electric field, and that's why the light will be blocked. There will be no light passing through this. Okay, so parallel, light completely passes through it. Perpendicular, no light pass through the analyzer. So this is simple, right? And for any other direction, we have a law by a scientist named Malus. let's understand it. When a plane polarized light is incident on analyzer, plane polarized light. So light that comes out of polarizer, it is called as plane polarized light because the electric field can oscillate in only one plane, okay, perpendicular to direction of propagation. This is polarized in that plane, plane polarized light, okay. So when plane polarized light is incident on analyzer, the transmitted intensity of light I is directly proportional to cos square theta. It is directly proportional to what? Cos square theta, where theta is the angle between plane of polarization and the transmission of analyzer. Okay, transmission axis, you can say pass axis. Okay, so the angle between transmission axis and the plane of polarization is theta. Then the intensity would be, intensity that is allowed to pass would be directly proportional to cos square theta. Okay, this is the law of Malus. So suppose this is unpolarized light, this is unpolarized light, then you put a polarizer in front of it, it will polarize the light. So intensity here would be I naught by 2. Now see, you put analyzer at an angle of theta. So here it is kept at an angle of phi, suppose. Then the intensity that is incident on analyzer is I naught by 2. What will be intensity coming out? It will be equal to I naught by 2 cos square of phi. Right? It will be I naught by 2 cos square of phi. So now this is easy to understand. See how? So this is suppose the electric field. Okay, intensity of light is due to the electric field. So now you can resolve it along two components. So this angle is theta, suppose. This is E sin theta and this would be E cos theta. And then we know that the intensity is directly proportional to amplitude square. So intensity of light is directly proportional to what? Electric field square. Okay. So this is transmission axis. This is the component of electric field parallel to transmission axis. So this component is allowed to pass. So what component is passed through the analyzer? It is E cos theta. So intensity here is suppose I. Therefore, because I would be directly proportional to what? E square. Okay, I is directly proportional to E square. Okay, or let's say it is I naught. I naught is directly proportional to E square. And intensity that is passed through the analyzer, it would be directly proportional to this component square only, because now only this component is left. Okay, perpendicular component is blocked, and therefore I is proportional to E cos theta square, that is E square cos square theta. And therefore if you take ratio of this one with this one, you will get I is equal to what? I naught cos square theta. Okay, I naught cos square theta. This thing is clear, everyone? Yes, no? Right, very good. So then this is the Malus law, easy to understand. Okay, and then next one is Brewster's law. This is also related to the polarization. Okay, another law related to polarization. So suppose this is incident light, this is unpolarized light, and it passes from a rarer medium to a denser medium. Okay, this unpolarized light passes from a rarer medium to a denser medium. Then what happens? So now if you incident it at a particular angle, so suppose this is incident unpolarized light. Okay, it is unpolarized. Okay, not plane polarized, etc., completely unpolarized. Then if you make it incident at a particular angle, then what will happen? The reflected light would be completely plane polarized. Okay, the reflected light would be completely plane polarized, right? And the refracted light would be partially polarized. It would be partially polarized. So what are the observations when this thing happens? So observations are that the reflected ray and the refracted ray will go at 90 degrees to each other. Okay, the reflected ray and the refracted ray will go at 90 degrees with respect to each other. Okay, and this angle theta is suppose the incident angle of polarization, it's IP. Okay, theta, when theta is equal to IP, okay, IP is angle of incidence for the reflected light to be polarized, that's IP. Okay, so then the refractive index of the second medium with respect to first medium, mu, would be equal to tan of IP. Okay, how will you find out IP? So mu is equal to what? Tan of IP. The refractive index of denser medium with respect to the rarer medium would be equal to tan of IP. Okay, is this thing clear? This is the Brewster's law. Yes, no, clear, not clear? Right? Okay, so now then let's see some problems based upon this thing. So the Brewster's angle IB, okay, they are calling it IB, for an interference should be, interface should be, sorry, not interference. The Brewster's angle IB for an interface should be, tell me. So you have tan of IP is equal to what? The refractive index of denser medium with respect to rarer medium, right? And you know that mu is, this refractive index must be greater than 1. So tan of which angle is 1? So we know the tan of 45 degrees is equal to 1. Okay, and the value of tan goes on increasing from there, right? Tan of 30 degrees is what? It's 1 by root 3. It's less than 1. Okay, so if you go below 45 degrees, then tan of an angle will go on decreasing. If you go above 45 degrees, it goes on increasing. Okay, so 45 degrees to what? 90 degrees at max, because tan of 90, tan 90 is what? It's infinity, right? And therefore, what would be the angle? So this angle must be equal to what? It must be greater than 45 degrees and it must be less than 90 degrees. Okay, so 45 degrees is less than IB, it's less than 90 degrees. Very, very simple, right? This is from the NEET 2020. Okay, this is clear. Let's see next problem. So two polarites P1 and P2 are placed with their axis perpendicular to each other. Unpolarized light I0 is incident on P1. A third Polaroid P3 is kept in between P1 and P2 such that its axis makes an angle of 45 degrees with that of P1. The intensity of transmitted light through P2 is, okay, two Polaroids P1 and P2 are placed with their axes perpendicular to each other. Unpolarized light I0 is incident on P1. A third Polaroid P3 is kept in between P1 and P2 such that its axis makes an angle of 45 degrees with that of P1. The intensity of transmitted light through P2 is, okay, tell me what will happen. So see what's given in the question. Two Polaroids P1 and P2 are placed with their axis perpendicular to each other. So this is your first Polaroid kept here. Then this is the third Polaroid. Actually they are calling it second Polaroid. So it's kept here. Oh, okay, so it is like this. So their axes are at 90 degrees with respect to each other. Or let's draw it this way only. Okay, this is third Polaroid. So now a third Polaroid P3 is kept in between P1 and P1 and P2. Third Polaroid is kept between P1 and P2. So suppose it is this one, which makes an angle of 45 degree with that of P1. This is not good. All right, so this is our Polaroid, third Polaroid. It makes an angle of 45 degrees. So the intensity transmitted through P2 is, tell me, how much of intensity will pass through P1? So suppose there is unpolarized light like this. Okay. Then the light passing through P1 would be polarized in this direction. But if original intensity is I naught, what is intensity coming out of the first polarizer? It's I naught divided by 2, right? We know for first polarizer, the intensity coming out would be equal to I naught divided by 2, right? The next one is at an angle of 45 degrees with respect to the first one. So what would be intensity coming out of this one? This is at 45 degrees. So intensity that's coming out of this one would be I naught by 2 cos square of 45, right? Okay, so what is cos of 45? So we know cos of 45 is 1 divided by root 2. Okay, so intensity coming out of this one would be I naught by 2 cos square of 45 means 1 by 2. Okay, so it will be equal to I naught by 2 times 1 by 2 means I naught by 4. And this one is at 90 degree with respect to first one, means it is at 45 degrees with respect to second one. So therefore the intensity that comes out, let's call this I prime. So I prime would be equal to what? This is equal to I naught by 4. Then intensity coming out of P2 would be equal to I naught by 4 multiplied by cos square of 45 degrees, because this one is at 45 degrees with respect to this one. Okay. So cos square of 45 is 1 by 2 again. So what would be the resultant intensity? It's I naught by 8. So that is the answer. Right? This is clear. This is very simple, right? Okay. Good. Let's see next one. Which of the phenomenon is not common to sound and light waves? Tell me. Interference, diffraction, coherence, polarization. It's option D, polarization. So polarization can happen with the transverse waves only. Good. It cannot happen for longitudinal waves. Okay. Longitudinal waves cannot be polarized. Only transverse waves can be polarized. Okay. So light is a transverse wave, sound is longitudinal wave, so it cannot be polarized. So this is the answer. Okay, good. So then this is the end of this chapter. Okay, so wave optics is complete, right?